Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have introduced started with the 4 subspaces connected with the given matrix of order m cross n, and we have discussed about the range space of the matrix and its transpose. So, in this lecture we will continue with that one. So, in the previous lecture we have discussed that suppose we have a matrix A that is of order m cross n, and then from here we can define a linear function that is A x, that is m cross n, and this is vector coming from n cross 1, and suppose this is after getting this value it is becoming m cross 1. So, it is a map from, so A we can define a map, a linear map from Rn to Rm, because my function x is belongs to Rm. And then we have discussed that the range space of the matrix A, it is a subspace of Rm, and the range space of A transpose is a subspace of Rn. So, this one we have discussed, and now, so after discussing these two things we want to go further and we want to find out what will happen if we have a equal range. So, in this case suppose we have for two matrices A and B of the same shape. Same shape means that should be of the same order, then the first is that the range space of A transpose is equal to the range space of B transpose, and this is possible if and only if A is row equivalent to B. So, that means row equivalent. It means by taking the elementary row operation we should be able to start from A and we should be able to get the B, then it is called the row equivalent matrices. Second one is then the range space of A is equal to range space of B if and only if A is column equivalent to B. So, it is the column equivalent means in this case we are taking only the column operation and map transforming from A to B by the elementary column operation. So, this is the column equivalent. So, this is because why we are doing this one, because in this case suppose we have two matrices and one matrix is row equivalent to the another matrices, then they are going to produce the same range space of A transpose is equal to range space of B transpose, and range space of A will be the range space of B. So, these things you have to keep in mind, and now we know that since we know that if I from the theory of row echelon form, we are always transferring the matrix A into some matrix U by the transformation P. So, where this is a row echelon form. So, then we say that A is row equivalent to the matrix U, and where P is a non-singular matrix. So, P is basically made up of all the elementary operations that we multiply, pre-multiply the matrix A. So, this will be more clear in the example. So, from here we know that A and U is row equivalent, and from there also we can say that the rank of A is equal to the rank of U. So, that we already know. So, now if you see very sincerely from here that when we starting from the A, then we always take the linear combination, some linear combination of the rows of the matrix A, and then after doing this linear combination we get U. So, from here one thing we can see that the rows of U are basically made from the linear combination, some linear combination of the rows of A. So, that is why we are able to discuss these things for range space of A transpose is equal to range space of B transpose. Now, we know that the range space of A transpose is spanned by non-zero rows, spanned by the non-zero rows spanned by rows corresponding to non-zero rows in U. It means we start with A, transform into U by some elementary row operation P, and in this U, whenever we have a U and in this whatever the non-zero rows are there, so the corresponding non-zero rows I will find out the rows in A. So, that will be these rows will span the range set of A transpose. Okay, so, these things is there. So, let us prove this one, the first one. So, we only prove the first one, the second one will follow the same. So, proof for first one. So, let A is a row equivalent to B implies there exists a non-singular matrix P such that PA is equal to B. So, this is given to me, and from there I can find PA is equal to B. Now, let I take some vector y belongs to the range space of AT. So, which implies that there exists some x such that A transpose x is equal to y, because y is belonging to the range space of this one. For some x I will get this value. You know that this A is m cross n matrix, then A transpose will be n cross m. So, this x will coming from Rm and this y is coming from Rn. Now, so this one is there. So, from here you can find that I just take the transpose. So, I can write x transpose A is equal to y transpose, just taking the transpose of this one. And now, from here I can write from here that y transpose is equal to x transpose A, and A is already there. So, I can write this as a x transpose, and A instead of A I can write P inverse P A. because P is a non-singular matrix. So, P inverse P will be identity matrix, and from there I will write X transpose P inverse P A, and P A is equal to B from the. So, from here I can write one vector Z transpose, and then it is divided by B, where Z transpose I am taking X transpose P inverse. So, it is the new vector we are introducing, Z transform. So, this is vector that is coming from X transpose P inverse, and from here you will see that. So, from here you can say that my Yt is becoming ZTB, or I can say that my Y become B transpose Z. So, that shows that Y belongs to the range space of P transpose. Okay, so, from here I started with a vector from the range space of A transform, and I showed that the same vector belongs to the range space of B transform. So, the same way I can go, I can take from Y and then moving the same way in the opposite direction, and I can from here I can go back the same way, and from there I can show that the Y will belongs to the range space of A transform. So, from here that first is okay, that A is rho equivalent to B, then we have showed that the range space of R A T is equal to the range space of B T, that will be same. Now, so this is converse is also true. So, similar things can be proved for the columns transformation, and that is we can prove for the second one. So, now based on this one we are able to say that if the two matrices are row equivalent, then their range space of A transpose is equal to the range space of B transpose, and so similarly things can be proved for a column transformation, which implies that the range space of A will be same as the range space of B if and only if A is column equivalent to B. So, this is the way we can do. Just we can take the transformation also of A transpose and B transpose, and then we can do the row operation, the similar things will come. So, this is the proof we can have. So, after this one there is one more one note, that two sets, suppose I take two sets A1, A2, AN, or maybe I should take R, two set this, and suppose I take the another B1, B2, BS that belongs to Rn. So, I am taking the R number of vectors here and S number of vectors here, that is lying in the NR, that span the same subspace if and only if the non-zeros rows of EA. So, EA I am writing here. So, what is the EA? It is reduced row reduced row echelon form of A. So, if the non-zero rows of EA agree means same with the non-zero rows of EB. So, that is the reduced row echelon form of B, where A and B are the matrices containing AIs and BIs as rows. So, can span the same subspace if and only if non-zero rows of these agree with the non-zero rows of these when A and B are the matrices containing AIs and BIs as rows. So, it means, what is the meaning of this? It means that I will take a matrix A and this will be A1, A2, AR. So, I will take this as a row and another matrix I will take B, and that will be B1, B2, BS. So, it contains S number of rows. Then I will transform A into EA by elementary row operations. B I will transform into EB. So, that is also row equivalent, elementary row operations. Then it says that if EA is equal to EB, if you know non-zero rows, so it is talking about only non-zero rows. So, if non-zero rows of EA is equal to non-zero rows of EB, then they will span the span of A1, A2 up to AR will be same as span of B1, B2 up to BS. So, that is our. So, these things is, we will take one example, but here we can just do the proof. So, proof is very easy because just we have to take that. So, the span of A1, A2, AR is equal to span of B1, B2, BS. Now, suppose we have a span of this is equal to span of this. So, definitely it implies that each AI can be written as linear combination of BIs, because the range span of this one is basically contains all A1, A2, AR, and that also contain B1, B2, BR. So, each of AIs can be written as a linear combination of BIs. Similarly, each of BI can be written as linear combination of AIs, because that we have taken, and from there I can say that the range space of A transpose will definitely equal to the B transpose, and if it is there, then this will also converse into. Okay, so these things we can check easily. So let us take one example, and then the things will be more clear to you. Now suppose I take the example. So let us say take the matrix A. Suppose I take first this matrix 1 2 1 1 3 6 3 4 2 4 2 2. Now this is a 3 cross 4 matrix. So A is a transformation from R4 to R3 and it is a linear transformation or linear function. Then now I will convert the A into the row echelon form. So first I will convert this into the row echelon form, and then from this one I will convert to EA, that is reduced row echelon form, and this is a echelon form, row echelon form. Okay, so from here now this is there. So from the A, what I do, I take minus 3 R1 and add to R2, and I take minus 2 R1 and add to R3 just to make this element 0, because this is the pivot element. Now if you see from here, I am taking linear combination of R1 and R2. Here I am taking the linear combination of R1 and R3, this one, and I get this matrix from here, that is 1 2 1 1, and this is 0. So because I am multiplying by minus 3, so minus 3 plus 3 0, minus 3 into, so it will be again 0, this will be also 0, and this will be minus 3 plus 4, it will be 1. Now minus 2 to 0, so it will be 0 0 0. Okay, so in this case now you can see that this is my pivot element, and next pivot element is this one. So from here I can say that, so you can see from here that I get a step like matrix, and this is my U. So that is a row echelon form, and from here I can also say that the rank of A is equal to 2, and that is equal to number of non-zero rows. Now from U, so this is my U 1 2 1 1, and where in the columns where these pivot elements occurring, so it is pivots. So this is called this, and this is called basic columns where the pivot element is appearing. So in this row echelon form, so I get this one 0 0 0 1 0 0 0 0. Now this is my pivot element, this and this, so I have to make this element 0 to make 0. So what I do is that I will just minus R2 plus R1. So, in this case also I am taking the linear combination of the second row and the first row, and I will get this matrix. So, it is 0, nothing will change, 1 2 1, I will multiply by minus 1 and adding here. So, it will be 0, and this is 0 0 0 1 0 0 0 0. So, here this is the pivot element and this is the pivot element. So, all other elements in that pivot column are 0, here also it is 0. So, this become EA, and this EA is called reduced row echelon form. Why it is called reduced? Because the number of elements are reduced, non-zero elements are reduced in the given echelon form. So, that is why it is called the reduced row echelon form. So, this is my EA. So, now from here I can say that the number of non-zero rows are 2. This is the non-zero row and this is the non-zero row. So, this is non-zero and this is non-zero. Okay, so, from here I can say that the range space of A transpose, if we take the range space, so it is spanned by the non-zero rows corresponding to non-zero row. So, it is 1 2 1 1, one vector, this one first row, and the second row 3 6 3 4, this one. Now, it is a span of this one, and from here I can also say that it is also span by 1 2 1 1 and 0 0 0 1. Because if you see from here, then you will come to know that this vector, the last vector, is coming by taking the linear combination of these two vectors. First vector is same, this and this is same. So, we take the linear combination of these two vectors, whatever the I have taken this linear combination, then I go to the second one. So, second one is here. So, this linear combination I have taken and I got this one. So, it basically the linear combination of these also contain this vector, and also from here also the rows, the non-zero rows, non-zero rows are linearly independent. So, basically these and these two vectors are allied, and also these and these two vectors are also allied, and this vector is a linear combination of these two vectors. So, from here very easily we can check that the span of this vector is same as the span of this vector, and from here I can also say that the dimension of range space of A transpose. So, that is the dimension of the range space of A transpose. So, that is equal to the number of linearly independent vector appeared in this one. So, that is equal to 2, and that is equal to the rank of matrix A. So, that is equal to the rank of the matrix A. So, from here we can say that the dimension of R A transpose is equal to the rank of A, this one. Okay, so, based on this one we are able to show. And this can also be written as also we can check that range space of A transpose is same as the range space of EA transpose, because the matrix A is row equivalent to EA, because EA is coming by taking the elementary row operation. So, that is coming from here, and just now we have done one theorem in the starting one, that first one. So, it shows that if A is row equivalent to B, then the range span by the rows is same. So, these things we can implement here from this one, and that we have also seen that how the vectors of EA are coming by taking the linear combination of the column, the rows of EA are coming from the taking the linear combination of the rows of A, and we also checked that the rank is same and their dimension is 2. So, that also we can see from here. Okay, so we stop here today. So, in the today lecture we have discussed that if the two matrices A and B, they are row equivalent, then the range space of A transpose is equal to the range space of B transpose, and if they are column equivalent, then the range space of A will be same as the range space of B, and then we have discussed one example based on that. So, in the next lecture we will continue with this one. So, thanks for watching. Thanks very much.